Rates of cardiometabolic diseases are climbing globally, despite decades of public health dietary advice. The failure lies in the foundation of the advice itself. It treats the entire population as a single biological entity. Historically, dietary guidelines were constructed for an era of food scarcity. The objective was simply to prevent baseline nutrient deficiencies using generalized rules, which relied on highly inaccurate, memory-based food logs. This chart compares traditional and personalized nutrition. On the left, we see that historical baseline. But modern clinical care faces an entirely different threat: chronic diseases like obesity, diabetes, and cardiovascular failure. To manage these modern diseases, the target moves from population averages to individualized interventions. We map a patient's specific genetic variability directly to their diet, leveraging advanced bioinformatics and predictive models. Executing this transition requires processing massive, continuous streams of patient genomic and environmental data, and it must be done without fracturing the existing clinical standard of care. This diagram introduces the unified model of precision health. It relies on 3 data inputs: a static genomic twin, a dynamic metabolic tracker, and daily environmental habits. All 3 feed directly into a centralized AI and bioinformatics core. Preventing modern disease is no longer a dietary guessing game. It is a complex data processing problem that requires an entirely new clinical architecture. We start at the molecular level. Identifying inherited risk relies on pinpointing single nucleotide variants, or SNVs, within a patient's DNA. This diagram illustrates the SNP effect. A standard genotype processes nutrients normally, but a single DNA alteration can block that metabolic pathway, requiring targeted intervention. Consider the SGK1 variant. Carriers exhibit increased systolic blood pressure on high-salt diets. A generic low-salt guideline is medically insufficient to protect them. But raw genomic data has a severe limitation. It is static. A DNA swab reveals a patient's inherited risk profile, but it tells us nothing about their real-time biological reality. This graphic displays the multi-omics funnel. To decode how the body reacts, the system filters raw data through transcriptomics for gene switching and proteomics for altered protein profiles. Finally, metabolomics produces the individual phenotype, the observable health status used for precise dietary adjustment. A patient's genetic blueprint is functionally useless without this continuous multi-omic filtering to measure how their body responds to its environment. Translating that continuous multi-omic data stream into actionable clinical insights requires distinct artificial intelligence modalities. This matrix maps the AI toolkit across nutritional applications. Machine learning handles metabolic prediction and risk stratification by finding patterns in massive datasets. Deep learning handles food image recognition and portion estimation. Applying computer vision for automated caloric tracking generates immense industry excitement, but deploying it in a medical setting demands strict clinical validation. This diagram charts the GoFood processing pipeline. A smartphone photo enters a deep learning network for recognition, outputting real-time macronutrients. In reality, the system hits hard limitations. It struggles to deconstruct blended dishes, fails with hidden ingredients, and suffers variance from environmental lighting. There are equally severe risks in deploying natural language processing, or LLMs, for dietary coaching. They lack clinical nuance and are highly prone to hallucinating medical information. AI algorithms are unmatched at data synthesis at scale. But they fail consistently at recognizing contextual, real-world variables, rendering them dangerous as autonomous clinical replacements. Because of these strict limitations, the anxiety surrounding the complete automation of dietetics is clinically invalid. This matrix compares an AI avatar versus a human clinician. An avatar provides 24/7 accessibility and rapid caloric estimation. But moving down to the red marks, it completely fails at managing complex comorbidities, providing psychological counseling, and ensuring medically safe guidance. The mandated solution is a collaborative model known as augmented dietetics. It is based on task shifting rather than professional replacement. This workflow isolates technology to the left AI domain, handling automated tracking, real-time metabolic synthesis, and basic triage. This frees the practitioner to operate exclusively in the human domain, interpreting data, adjusting protocols for comorbidities, and providing the empathy required for lifestyle change. True precision nutrition empowers the patient with high-capacity technology, but strictly guides that technology with human clinical judgment. Even within this augmented workflow, deploying AI at a clinical scale introduces severe structural and ethical vulnerabilities that must be mitigated. This graphic illustrates the threat of algorithmic bias. Current models are trained almost exclusively on Western, high-income food logs and demographics. When deployed globally, they misinterpret cultural diets, leading to inaccurate nutrient assessments and medically inappropriate recommendations. Clinicians also face the black box threat, where deep learning produces uninterpretable reasoning, degrading clinical trust, along with severe privacy vulnerabilities when processing sensitive biometric patient data. This flowchart outlines proactive ethical mitigations required to secure the clinical environment. These threats demand specific engineering solutions prior to commercial adoption. To combat the black box threat, developers must mandate explainable AI frameworks that provide confidence scores and transparent algorithmic pathways. To secure data privacy, systems must implement federated learning. This protocol allows global models to train using robust anonymization on local devices, updating the algorithm without ever extracting raw, legally protected patient data. Unchecked algorithms threaten to widen global health disparities. Ethical oversight and inclusive validation must be engineered directly into the baseline architecture. Assessing the current landscape of AI dietetics reveals an abundance of short-term usability pilots. However, there is a critical scarcity of Tier 3 randomized controlled trials validating hard clinical endpoints. This timeline illustrates steps to standardized clinical integration. First, adopting reporting frameworks like Consort AI eliminates opaque designs. Next, multi-site trials validate demographic adherence. Finally, interoperability is the ultimate bottleneck. Precision tools must embed directly into electronic health records rather than remaining isolated consumer apps. Technology only becomes medicine when it is transparent, interoperable, and proven through rigorous longitudinal clinical trials. Modern health strategy relies equally on processing molecular data and maintaining rigorous human oversight. This graphic displays the definitive verdict on automation anxiety. AI will not replace dietitians, but dietitians who use AI will replace those who do not. Integrating these tools safely requires curriculum evolution and proactive governance. These remain the responsibilities of human practitioners, not technology companies. Clinical outcomes now depend on the integration of biological data with human intervention, moving past static genetic observation toward active disease prevention.